Okay, I should start. Thank you, Gerald, for the introduction and giving the house rules. Thank you, all of you who are signed up and currently listening. Good morning, good afternoon, good evening, depending on which time zone you are in. Today I'm going to talk about graphene-based materials and thin films. So let's see. And excuse us for any technical glitches here. I think that was just signed up from Skype. So let me introduce first the institution I belong to. I'm with Case Western Reserve University here in Cleveland, Ohio. It's rainy outside, but in a nice day, this is how our place looks like. We're situated in the University Circle, close to the cultural heart of Cleveland, Ohio, home of the Cleveland Orchestra, Cleveland Museum of Art, Cleveland Clinic, and of course Case Western Reserve University. Our university was founded in 1826, but at the same time, a lot of famous alumni, Nobel Prize winners, have been part of our lot. Even the founder of Dow Chemicals, Henry Dow, started here at Case Western Reserve University, and Dow Chemical Company was first actually incorporated here in Cleveland, Ohio. I'm with the Macromolecular Science Engineering Department. Another term for that is Polymers Science and Engineering. And you can see there a picture of my group. And we are located at the fifth floor of the Kent Hale Smith building. We also have in our campus a $13 million facility called the Think Box, which is a rapid prototyping 3D printing additive manufacturing facility, most especially open to students to bring their ideas into devices, prototypes, and actual working parts. Some companies have been founded actually by students who work with this creativity center, and especially for us, we use this as a laboratory for testing new materials and composites. I'm also the director of PetroCase, which is a consortium dealing with the needs of the oil and gas industry for high-performance materials, coatings, fluids, and sustainability engineering. We'll be happy to communicate with you offline more about this operation. So being a professor, it's still publish and perish for us, so we have a number of research involving that of nanomaterials, thin films, stimuli responsive systems, patterning, strategies, etc. that are shown here on some of the cover pages we have accomplished in several high impact factor journals. On the other hand, we are very versed with the needs of industry, and through the years we've worked with a number of companies, both the research and development side and as well as consulting. Really, I believe that what we produce in a university essentially are platforms that need to be useful for society, the bridge of which is through applied research or engineering, which can mean that we develop things that are solutions to the toughest problems there, as well as developing new markets to innovation. So we are all connected in this global community, whether we're dealing with technology or limited resources. All we want to do is accomplish a way that we can make relevance of what we see and what we do not see. So I'd like to start by showing that in this grand scheme of things, we are dealing merely with what we see, but in reality, we have both the radio and nuclear spectrum of the full electromagnetic spectrum that we can utilize and innovate. And that brings us towards nanotechnology. So when we talk about inspired creativity, we are looking at things that have been part in nature for a long, long time, and we are but in the discovery mode and trying to adopt things that have been around for a while into man-made goods or innovation. And that is really the essence of bringing nanotechnology to more useful things for society. So really it is a multi or interdisciplinary approach, taking the best that we can come from the chemistry side, physics side, as well as the engineering side, and utilize it for new products, new methods, new businesses, and so on. So let's start by looking at nanostructuring. So when we refer to a nanomaterial, we are of course referring to a scale, a billionth of a meter, 100 nanometer to submicron level even, where we have building blocks that can be structured in a bottom-up approach. On the other hand, when we talk about lithography, microprocessors, different types of patterning methods, we are taking what we observe in the bulk or the macroscopic side and then patterning it or structuring it towards the nanoscale. We call that a top-to-bottom approach. So either way, whether you're a top-to-bottom or a bottom-up approach, nanostructuring involves that of designing by self or directed assembly something new. I like to show this graph because polymers play a very important role in nanoscience. Despite what we hear about nanoparticles, metal oxide nanoparticles, or even the theme today, which is carbon-based graphene nanomaterials, polymers play a very important role because they can be utilized as nanostructured films or nanostructured colloids, or basically interfacial science where we find relevance as films and particles. So for example, as ultra-thin films, we can order these polymer materials or even inorganic nanomaterials either in a layer-by-layer approach, chemisorb approach, or evaporated methods. For example, we have pioneered many things involving that of electropolymerized or electrodeposited patterns, as well as grafted polymer brushes, which I will not have time to discuss more today, perhaps another seminar. So we go straight to carbon and its allotrope. Previous to the popularity of graphene, many researchers have dealt with nanotubes, fullerenes, single-walled, multi-walled nanotubes, carbon fibers, etc. So graphene is but a part of a grand scheme dealing with carbon-based materials and allotropes. And graphene has many important advantages. So first of all, graphene is the base material by which higher ordered structures can be formed with short and long range ordering, whether we are dealing with nanotubes, which are basically rolled up graphene, or we are dealing with flat platelet structures, which is very well known as a derivative that can be harvested from graphite. Others have looked at utilization of plasma and metal catalyzed methods to produce graphene structures, pyrolysis, etc., which we will talk about in the next few slides. But essentially, graphene is a class by itself compared to other carbon-based materials. Because of its high aspect ratio, meaning very thin but very wide in area, it has functions like moisture barrier, high electrical conductivity, density 4 times lower than copper, meaning lighter than copper but more conducting at times compared to copper, high thermal conductivity. It has a lot of surface area, as you can imagine, so nanomaterials have what we call surface to volume ratio advantages. Lower density than steel, but it can be up to 50 times stronger. Readily functionalized surfaces or edges. It can be dispersed in many polymers and solvents and can be utilized with high loading in nanocomposites. All of these interesting measurements, of course, is related to the sample geometry or the way the material itself is oriented. meaning when we say something is stronger than steel, you have to take it with a grain of salt, meaning how was it actually measured. So the properties of graphene is very different tangentially or in parallel with the plane of the graphene material itself. So deposition methods as films. One can prepare them from graphene sheets exfoliated from graphite and prepare them as materials that can be floated at the air-water interface, in which case we can deposit them by LV deposition. We can functionalize the graphene oxide together with polyelectrolytes and deposit them on a layer-by-layer fashion. You can go graphene, the reduced form of graphene oxide, and prepare them as a crystalline form, monocrystalline form, although that is difficult by CVD methods. And in our case, we've specialized in methods for forming films by electrodeposition. Graphene has many potential applications. As you can see here, it can be prepared as a film, in which case it can be used for flexible electronics, actuators, electrochromic devices, transistors, other applications in flexible electronics, or in general, solid-state devices, whether it's display, pressure-sensitive, or other smart applications. On the other hand, what we have discovered is they have actually interesting antibacterial properties, in which I'll have time to show the results today. For example, as a barrier material, a one-layer graphene coating on a copper-based metal coin can actually be enough to mitigate corrosion. That is a very, very thin film of graphene nanosheets overlaying a copper is enough to prevent the material underneath the graphene from being oxidized. On the other hand, we have found that they have antimicrobial properties, able to kill E. coli, Bacillus, S. albicans, and other types of gram-positive and gram-negative bacteria or pathogens, but is not as harmful to mammalian cells. Gas barrier properties means that we can make them very thin, orient them, and investigate a tortuous path for oxygen and other types of gases to diffuse through this barrier material. In other words, these are excellent for packaging applications. That means that if this can be incorporated in a extrusion or blow molding process or deposited over a certain wide area, then one can have both this barrier function along with the interesting electrical conductivity, thermal conductivity properties as well. In fact, if you make them very thin enough, you can have a transparent conductor as well. Now, in terms of thin application, so they have been used in photovoltaic devices, memory devices, microelectrodes, even organic light-emitting diodes, either doped as a part of the whole transport or electron transport material. On the other hand, this figure shows that patterning or templating of graphene is a very important direction. It's because graphene is quite conducting, very conducting indeed, comparable to copper. And that actually limits some of its applications as a semiconductor. And patterning it is a method of controlling the degree of conductivity. How do we make graphene? Graphene can be prepared with many ways, but the graphene that has been reported in literature is actually an exfoliated form of graphite. So graphite, if you experiment with this, if you take a scotch tape and then on a graphite you start sticking that scotch tape and peeling it off, you notice that when you peel off the scotch tape, some material is adhered to the scotch tape surface while keeping the substrate intact. If you do this so many times, n number of times, it may just be possible to obtain a one-layer sheet of graphene. So this method is basically an exfoliation method. However, other methods of making graphene could be in the form of carbon segregation, on a metal surface, CVD methods, plasma deposition methods, metals except, for example, catalyze the formation of these carbon clusters, forming wide areas of pi-fused ring systems. In fact, another way to make graphene is based on precision synthesis of coronene and graphene-like structures by organic synthesis routes. Now, this one is quite interesting because you can use precursor routes. However, to obtain very pure forms of highly symmetrical graphene-like structures can entail a very expensive synthetic method. So they're very good model compounds. Now, what has been utilized mostly in laboratories in a way to harvest graphene and graphene oxide in larger quantities is through exfoliation methods, which is basically taking graphite plates, using a oxidative in order to disperse the graphene, and in the process you convert graphene to graphene oxide. Now that's very important because the graphene oxide actually makes it soluble to solvents, and this can be accelerated by the use of ultrasound or even microwave techniques. So as you can see here, graphite, when sonicated, can be broken into monolayer graphene flakes. They can be dispersed in organic solvents. Graphene oxide are actually very well dispersed in aqueous solvents, and to transfer them to organic solvents or more nonpolar organic solvents requires a bit of complexation and modification. That is, you can use surfactants as well to aid their dissolution in a variety of solvents. So our first paper back in 2011 involved that of taking the graphene oxide precursor and complexing it with a polymer called polyvinyl carbazole. Now you notice that the structure of PVK has a carbazole ring, which actually complexes through pi stacking or pi-to-pi interaction with the graphene, dispersing it very well, such that we can make gels, we can make solutions, and we can use this to electrodeposit the PVK graphene oxide complex to form thin films. The graphene oxide is prepared by sonicating, heating it up, and dispersing it with a surfactant. This is actually a method that we patented, but also is available in literature, a method for making high concentrations or loading of graphene oxide in a solution. So here you can see that graphene oxide is basically the oxidized form of graphene. The oxidizing agent causes the rupture of the double bond to form hydroxyl units, carboxylic acid units, epoxide units, in such a case that you have this functionality that populates the surface and the edges of graphene oxide, making it or rendering it soluble to a variety of solvents. On the other hand, if you want to get back the more conducting form, then you introduce a reducing agent such as hydrazine, which then converts the graphene oxide to the more conducting form of graphene, as shown in this picture, going from a brown colored solution to a dark black colored solution, which indicates a more conducting form, graphene. You can also follow this type of dispersion and reduction either by the methods of thermogravimetric analysis, infrared spectroscopy, and XRD. So with thermogravimetric analysis, you will know how much oxygen is incorporated on the graphene. The XRD gives us a picture of the degree of exfoliation and periodic stacking. The FTIR as well gives us the functional group present on the graphene oxide, and it's absent with the pristine material or a graphene derivative. So here you see we are successful in dispersing graphene oxide to a variety of polar solvents. They have varying degrees of solubility and stability. On the AFM image one, you can see the analysis we've done on a single sheet with a thickness of about 1.2 nanometer, indicating that we indeed get a almost monolayer, or if not bilayer, derivative of the graphene. And then the AFM image on the right shows that we have non-exfoliated native graphite starting materials, where you can see the lamellar sheets stacked up on the native graphite. Again, from XRD and absorbance measurements, this case, we have the graphene oxide and the complex graphene oxide with PVK. Here we can see that the graphene oxide shows a high degree of periodicity, which by dispersing it with the PVK is lost. On the other hand, the absorbance measurement shows that the Carbazole group present on the material shows absorption near the UV visible region, or towards the UV. On the other hand, the graphene oxide itself does not have any absorbance in the visible region. Likewise, we can use thermogravimetric analysis and FTIR to confirm the complexation. The PVK typically degrades faster at around 400. The graphene oxide PVK has a degradation greater than the PVK alone. On the other hand, the graphene oxide shows degradation all the way to 800 degrees C, or it's more stable than either the complex or the polymer itself. FTIR as well confirms the form of graphene oxide we have by the formation or the presence of absorption in the 3400 region. Now, electrochemically, this is relevant because the polyvinyl carbazole actually has an electroactive monomer species in the form of the carbazole. That means the carbazole can cross-link and bring down the graphene oxide to form films, as shown here in the AFM. And we can follow this electrodeposition process by looking at the cyclic voltammogram up to 50 cycles. So we can see here the oxidation and reduction wave. So as we deposit the film together with the polyvinyl carbazole, there appears a peak at the 400 to 600 region, indicating the polymerization of the carbazole units to form polycarbazole, whereas a simple drop-casted unit without the electropolymerization process only shows the carbazole peak, as here. So this method, in fact, we patented as a way of pinning down the graphene oxide by using a precursor polymer that can form a barrier material, an electroactive barrier material as well, deposited on a conducting substrate. We actually have several uses of this, and I'm not allowed to show them because of some patent disclosures, but essentially this is a way of modifying conducting surfaces or making a coating which can have some anti-corrosion properties. We developed back in 2011 a method which we call templating using colloidal particles. As shown here, we can make an array of colloidal particles of 500 nanometer spherical polystyrene made from emulsion polymerization. When you layer them two-dimensionally, the material will deposit on the interstitial spaces of these colloids, forming a pattern which can be developed by removing the polystyrene particles. So in this case, by removing the templated polystyrene, we end up with a honeycomb structure. We end up with a half dome and full dome structure as well. And this simply means that we can take any electrodeposition method and template them using these particles. So indeed, we did that with PVK, polymer, and the graphene oxide. We deposited them around these colloidal particles to produce a pattern which looks like this. So what you are seeing here is a conductive form of the PVK graphene oxide complex that was deposited electrochemically around these colloidal spheres to produce this honeycomb structure. And we have found interesting uses for this. One of it, well, first of all, this shows the characterization we did based on the cyclic voltammogram, the absorption, as well as the vibration spectroscopy methods, revealing that of the PVK film and the graphene oxide PVK complex. So what we have found is this type of patterns can be useful for gating or limiting the electrochemical behavior of ions going through a surface. In other words, this has a potential for use as membrane materials that are electrochemically tuned. The XPS or X-ray photoelectron spectroscopy results shown in this part of the view graph confirms that we have the ITO substrate that can be observed because of the presence of the holes during the templating process. Now let me take you to another form of graphene oxide. In this case, we modify the graphene oxide because of the reactive species present, whether it's the alcohol or the carboxylic acid. We can take this epichlorohydrin derivative and graft more carboxylic acid groups on the surface. This means that we can do more esterification or amidization chemistry on graphene oxide. A good example is by making an amide linkage of this bifunctional Carbazole unit. We end up with a dendron-like structure surrounding that of the graphene oxide. Now, why we will do that? Simply because we are interested in building in the electrochemical activity on the graphene oxide material itself without mixing it with PVK so we can make nice films. These are very stable modified graphene. We can essentially put them in various solutions. They do flocculate, but with simple agitation, they immediately go back to solution. And this is the spectra of the modified graphene oxide, as well as the fluorescence, indicating the fluorescence of the Carbazole units. By XPS, we can confirm that the graphene oxide was modified by the Carbazole groups. Here are TEM images of the graphene oxide and the graphene oxide that has been modified by the Carbazole. And here you can see that these are true exfoliated nanosheets that can be derivatized with an organic moiety along the surface. In fact, we can deposit this, electrodeposit this on pattern arrays and modify the wetting behavior of, let's say, an Egyptian oxide substrate, as shown in this contact angle. But nevertheless, the cyclic voltammetry method allows us to track the deposition of these platelets on the surface of the ITO to form this complex or patterned layer. Here is another picture of the material based on TEM images. SEM images we have as well, where you can clearly see the graphene oxide sheets incorporating a thin film on the ITO substrate with the edge. So basically, you can see here the graphene oxide sheets that were incorporated in this ultra-thin film layer. However, if we control the density and the number of cycles, we have a variation on the roughness as well as the homogeneity of this film. And you can clearly see here that the more material we deposit, or even higher concentration, the more agglomeration we observe with the film coating itself. So this chemistry actually allows us to do what we call nanomesh fabrication. So if we take the colloidal templating method, we can modify the graphene oxide surface and deposit, let's say, this Carbazole unit, and then remove the templated structures and then delaminate it from the surface. In principle, we can end up with a freestanding graphene nanomesh film that is ultra thin. Indeed, we were successful in patterning graphene oxide using this colloidal templating method. Here is an AFM image which shows the modified graphene oxide and the holes where we used to have the colloidal template. So basically the dark region here indicates where we deposited the Carbazole monomer, or rather polymer now, a graphene oxide in the middle of the pattern. So basically, this is a semi-conducting graphene oxide film. And then since then, we've tried to investigate methods of delaminating them and form freestanding films of graphene oxide sheets. Here, we have shown that we can disperse them, of course, with PVK. By TEM, you can show here the platelets of very good polydispersity. Here again, the solution or solvent qualities of the dispersed graphene oxide. In this case, we were interested actually in their antimicrobial properties. So what we did is we took this complex of PVK and graphene oxide, and then we used optical density measurements after exposure to bacteria. In other words, if we have more bacteria, we would have dead bacteria anyway, we would have a higher optical density, which is the case if we have the blank versus the graphene oxide versus the graphene oxide PVK. We can basically compare their ability to kill bacteria in one way. So in this case, the higher the optical density, the higher the time to reach the optical density at 600 nanometers right here. That means that we have more dead bacteria versus the PVK and control. Another way to look at it is by doing fluorescence measurements. So the bacteria itself can be tagged with FITC and TRITC, that is fluorescein and Texas red dye. The live bacteria is shown here as green. So we have the control, we have the PVK, we have the graphene oxide, PVK, and graphene oxide. What is interesting here is to see that the TRITC red, the dead bacteria is shown only on graphene oxide and PVK by these red platelets or structures, which indicates that PVK alone and the control does not kill bacteria. But graphene oxide and PVK kills bacteria because of this post-mortem analysis with TRITC red. And this can be represented here quantitatively by the total bacterial count as shown here in this graphical representation. Not only can it kill E. coli, but we have tested it with B. subtilis. We're now looking at albicans. So essentially, gram-positive and gram-negative bacteria, it can kill them, or it's toxic for pathogens. On the other hand, it's non-toxic for NIH3 T3 fibroblast cells. In other words, there's a high survivability rate for mammalian cells. So in this case, it's possible that the properties of graphene oxide pathogens by to mammalian cells, which can have implications as coatings for biomedical applications or even food packaging. Here we actually see the AFM image of the biofilm formation on PVK and ITO, which means that these are happy bacteria. On the other hand, the PVK GO shows very little, biofilm formation after a few days because of the presence of the PVK and graphene oxide. So believe it or not, I'm done. I probably have given you more questions to ask or more possibilities to think. Now I'll be happy to interact with you guys and be happy to answer any questions you may have. Thank you.
Great, thank you, Professor. So, just like as was stated before, there should be a questions module in the control panel for your GoToWebinar view. So go ahead and type in your questions there, and we'll be answering them in sequence. I'll, of course, read them out loud in case the entire group cannot see them. So we'll go ahead and spend a few moments here waiting for some questions to pour in. Thank you very much.
Several questions might be coming your way, Gerald, but I can state some points in terms of the graphene oxide community. It is one of the largest nano communities to date. The number of publications and even patents there have exponentially grown. A number of companies are involved with the supply chain of providing graphene oxide, either through the Hammers method or evaporative methods or catalytic methods. So it's safe to say that graphene oxide is making its way into mainstream and additive type of sources. So some of the interesting applications we would like to do or have been seeing is that they can be incorporated to plastic, thermoplastic, and formulations which may include paints, inks, and other types of fluid and low to high viscosity type of formulations. Look at it is by doing fluorescence measurements. So the bacteria itself can be tagged with FITC and TRITC, that is fluorescein and Texas red dye. The live bacteria is shown here as green. So we have the control, we have the PVK, we have the graphene oxide, PVK, and graphene oxide. What is interesting here is to see that the TRITC red, the dead bacteria is shown only on graphene oxide and PVK by these red platelets or structures, which indicates that PVK alone and the control does not kill bacteria. But graphene oxide and PVK kills bacteria because of this post-mortem analysis with TRITC red. And it can be represented here quantitatively by the total bacterial count as shown here in this graphical representation. Not only can it kill E. coli, but we have tested it with B. subtilis. We're now looking at albicans. So essentially, gram-positive and gram-negative bacteria, it can kill them, or it's toxic for pathogens. On the other hand, it's non-toxic for NIH3T3 fibroblast cells. In other words, there's a high survivability rate for mammalian cells. So in this case, it's possible that the properties of graphene oxide pathogens by to mammalian cells, which can have implications as coatings for biomedical applications or even food packaging. Here we actually see the AFM image of the biofilm formation on PVK and ITO, which means that these are happy bacteria. On the other hand, the PVK geo shows very little, little biofilm formation after a few days because of the presence of the PVK and graphene oxide. So believe it or not, I'm done. I probably have given you more questions to ask or more possibilities to think. Now I'll be happy to interact with you guys and be happy to answer any questions you may have. Thank you.
Great, thank you, Professor. So, just like as was stated before, there should be a questions module in the control panel for your GoToWebinar view. So go ahead and type in your questions there, and we'll be answering them in sequence. I'll, of course, read them out loud in case the entire group cannot see them. So we'll go ahead and spend a few moments here waiting for some questions to pour in. Thank you very much. Great, thank you. Okay, well, let's see here. It looks like there is another question, follow-up. What would be the advantage of functionalized graphene oxide over functionalized carbon nanotubes?
Yeah, very good question. We actually worked a lot with carbon nanotubes before graphene oxide because we had at that time, we thought the only material we can work with in terms of electrically conducting carbon nanotube species. That is, before graphene oxide or graphene became popular, carbon nanotube is the thing, or carbon nanotube is more popular. So what you have there, first of all, is a difference in aspect ratio and orientation. Graphene are platelets, whereas your carbon nanotubes are fibers or are cylinders. And that means the percolation threshold of any particular property can either be reached through networking in the form of the carbon nanotubes, and in the case of graphene oxide, it may be a function of layering. So in this case, the carbon nanotube can be dispersed as a composite material. Same with graphene. The interesting properties of a graphene composite typically shows up when you make very, very thin layers in which the graphene oxide or graphene material is oriented parallel to the surface of the substrate. On the other hand, the carbon nanotube, sometimes the properties are dependent on how it is aligned in one direction, anisotropy, or how it is networked within a structure. That is, if you're looking at both thermal and electrical conductivity, both types of orientation, whether it's networking or forming one-layered platelet sheets, is important in having a very high property value for both electrical conductivity and thermal conductivity.
Okay, and it looks like we have another question to follow up. Which one shows a better sensing property to volatile organic compounds? I assume that's in reference to the previous question. In gas sensing applications, would you recommend graphene oxide or carbon nanotubes?
Interesting question. Hard to choose. We have done a lot of work actually on both materials, and the merits, let's say, of a good sensing material is if you have a high contrast ratio between the on and off properties, meaning with or without the analyte present. The other is, of course, sensitivity. So sensitivity, selectivity, limit of detection, dynamic range, all of these are important figures of merit in assessing the performance of a sensor. So it's a hard question to answer. I would say both are equally interesting. On the other hand, in the side of conductivity, I would say graphene preparation tends to be less expensive, easier to form more conducting substances. On the other hand, with carbon nanotubes, one has to work with single-walled nanotubes to achieve very high levels of conductivity. Hello, Gerald.
Yes. Well, it looks like we've exhausted the current list of questions, Professor. I'm not sure if any more would be coming in, but again, we have left our email addresses. Mine is in the chat, and the professor's is on the title slide. If that's about it, I believe we've reached the end of today's session. What would you say, Professor?
Well, first of all, again, I thank you for being part of our webinar series. As you can see here, this is done partly to educate the community with the latest trends, research, of course, coming from our group, our expertise. But at the same time, I would like to thank Park Instruments, AFM, where you can see the importance of microscopy and probe microscopy techniques like AFM in characterizing nanomaterials. So I hope that you've learned something very useful today, and we'll be happy to communicate with you offline. Thank you for being part of our web.